Okay, so we are talking about chapter 5 on the topic of light. Light 101 is just kind of saying like, hey, if this was the course on light, here are the basics. So what is light? Well, light is electricity and magnetism that carries energy from place to place. It is a wave that oscillates as it travels. So there is a lot to unpack there. I'm not going to get into all of it. What I do want you to, especially if you've never heard a similar statement, if you have, that'd be great. But what I do want you to consider is that it is electricity and magnetism. So we can think about how light is going to have the properties of electricity and magnetism and how electrical and magnetic effects can make light. So light itself is neutral, unlike electrons. So we shouldn't expect light to be affected by an electric field. Or if you have like a magnet or a magnetic field, light won't bend as a result. But electricity and magnetism are able to make light. So a lot of the ways we talk about light being generated are going to involve a discussion of moving electrons for the most part, or wiggling atoms, or vibrating molecules. When light is shown like this, in this is kind of a popular type of figure, we're looking at the two components of light. So we'd be looking at the magnetic and electric components. So light carries energy from place to place. So it transmits energy. It, as you know, obviously can deliver heat. It can transform into different types of energy. So the energy is going to be conserved, but the energy of light can become potential energy. It can become heat. It can be changed into different types. Light is the only form of energy that can travel, at least the only form of heat that can travel through the vacuum of space. And so there's two other heat transmission mechanisms, which are convection and conduction. Convection is like movement of fluids, like hot air rising, and conduction is just like when you touch something hot and it feels hot, like metal conducts well, where like a ceramic doesn't conduct as well. And so those types of energy transfer, heat transfer, don't work in a vacuum because they require molecules or a medium. Light doesn't. Light can just move through the vacuum of space. And although we now know that space is not a perfect vacuum, there's always some molecules, even in the most low density sections of space. Those molecules aren't necessary for light to move. It moves in the gaps between the molecules just as well as it interacts with the occasional molecules in those low density pockets of space. How quickly it oscillates is called its frequency. So light has a frequency just like any repeating, event, any repeating phenomenon. So like you have the frequency of a pendulum swing. You can have the frequency of a vibration. Then you can have the frequency of a wave, like even a wave on a string. Think like stringed instruments and the frequency or frequencies of sound waves. And frequencies are measured in hertz. And a hertz, you've probably heard the term, is just 1/2 second. So it's just an inverse second. And it's how we measure frequency, which is how many times something happens per second, which is why it's 1/2 second. And light has a frequency. Their frequencies tend to be really high. For visible light, we're talking about frequencies in the billions of hertz. Radio waves are going to have lower frequencies, but they're still going to be in the millions or at least thousands. And what the frequency tells us is how much energy the light has. So there's a direct relationship between frequency of light and energy of light. In fact, the higher frequency, the higher the energy. In other words, high frequency light is high energy light. You will also see that we can talk about the wavelength of light and come up with similar rules, but they will be opposite. More on that later. One of the biggest things that you want to remember is that, and one of the few things that we already saw about light, is that it has a fixed speed. Light travels at the same speed everywhere in the universe. That speed cannot be passed. It is the speed limit of the universe, to describe it succinctly, and it's about 3 times 10 to the 8 meters per second. Here it is in metric units. And we would say, you could say this in words as 300 million meters per second. 300 million meters per second. It's an incredibly fast speed. Nothing, is comparable. If we think about other types of waves or velocities of, spacecraft or asteroids or even planetary speeds. How fast are we orbiting, right? Those are impressive speeds, but they're nowhere close to this. However, because space is so big, this is a limiting factor in terms of how fast information can travel from one star to another, or let alone one galaxy to another, because those distances are many thousands or millions of light years. And that's literally how long light takes to travel, as we talked about before. Okay. And it can travel in many forms, all the different types of light in the entire electromagnetic spectrum. An expression I'll use again if you're wondering, electromagnetic spectrum, what's that? Well, we'll come back to it. Basically, it's just all the types of light. So, mention wavelength of light. Well, here it is again. How far light travels, one oscillation is called its wavelength, often measured in nanometers. And that is a base unit, or I mean, it's not a base unit, but it's a version of the meter that is widely used because it's well suited to visible light, but it gets used for invisible light as well. So this would be light that is not part of the visible spectrum. Types of invisible light you've probably heard about are infrared light or ultraviolet, but also microwaves and radio waves. And some of those will be impractical to measure in nanometers, and we won't use nanometers. We'll just use meters or some other unit. But we'll definitely use nanometers quite a bit. A nanometer is equal to 1 billionth of a meter. So it's 10 to the negative 9 meters. So in scientific notation, 1 nanometer is 1 times 10 to the negative 9 meters. That's the length of a nanometer. And in the picture, a wavelength would be one complete oscillation. Here, let me change my color here and see it more clearly. So one complete waveform or one complete oscillation from beginning to end. So here I'll start right here, and I draw the light wave. So it goes down, and the light wave here it's a sinusoidal light wave. So it can be represented by a sine or cosine. Not responsible for that, but that helps you kind of, if you're wondering what this shape is. And so this right here, this would be one full wavelength in terms of this length along the axis. So like if I was interested in how long it was in the direction that it's traveling, that would be one wavelength. So that distance right there. And the letter we use for the wavelength is the Greek letter lambda, which is this that I wrote right here. Doesn't really look like any, letter in the Latin alphabet, so it's just a lambda. No other way to describe it. A weird curve and then a straight line. But that represents one wavelength. Okay, so here is the key formula that relates velocity, okay, or speed, wave speed, to frequency, wave frequency, and wavelength. And there's that lambda again, okay? Just a not like a italic version of it. All right, so this is a key formula for understanding light. It can actually be applied to any wave, except that this speed wouldn't be c, because c is the letter we use for light speed. Normally, if it was the speed of some other wave, we'd use v for velocity, but for light, we always use c as the specific letter that's reserved for light speed. I don't know why they chose c, but it's really only used to represent light speed. And so, unlike other ways where v can change, because like sound waves travel at different velocities depending on the density of the material that the sound wave is traveling through, and air sound waves tend to travel around 300 meters per second. Well, they travel at a different speed in a different atmosphere on a different planet, for example, different speed in water, right? But light doesn't. Light always travels at this same speed of three, this number right here, 3 × 10⁸ meters per second. So this is the constant on the left-hand side. F and lambda are not constants. But because they equal a constant, that means the relationship between the frequency and the wavelength, lambda, and we'll write it out. So lambda, LAMBDA, okay, so lambda so the relationship between F and lambda means that if you know one of them, you automatically know the other. Because, if your lambda is, 100 nanometers, and c is always 3 × 10⁸ meters per second, well, then you know what F is automatically because it has to be, whatever value you multiply, 100 nanometers, for example, by in order to get 300 million meters per second. So it's like, so you only need to know one of these two variables in order to know both of them. And that's a unique property of light. Because as I said, other waves you'd have to independently know the wave speed. Not so for light. Okay, so I'm doing on time. Good. So light is a wave. I think you know that by now. Okay. And here is a representation of the wavelength, like the one that I drew. Notice that when I drew the wavelength, I drew it from kind of where the wave intercepted the axis that represented the direction of motion, shown here as the v or velocity axis. And then I had the wavelength go until we crossed the second time to complete the shape of the wave. You can also measure wavelength from any point as long as you get back to the same starting point. In this case, they're measuring wavelength up on the top from peak to peak, or from trough to trough, where trough is just the opposite of the peak. So from maximum to maximum in both cases. Okay, so spatial distance between high or low points of a wave. The amplitude is how far the wave gets from the midline. So it's the maximum height of a wave. So when we talk about light, amplitude is directly related to brightness. And another word that I'll use is intensity. So greater amplitude light is brighter light or more intense light. Frequency is the number of times per second a wave repeats. So that could be if you stand in place, it's the number of complete wavelengths that pass by you in a given amount of time. That'd be one way to think about frequency. Or if you think about this wave kind of moving up and down, it's the number of times that it varies from peak to peak down the trough and back to peak per second. Because waves are both moving and and oscillating. And the speed is how fast the wave moves from place to place, which in the case of light is a constant. Right? And there's our formula. Notice here that they've replaced the c with v because that would be a general case for a wave, right? So like other than this parenthetical section here where it says brightness for light, everything on this slide could apply to any type of wave. Like an ocean wave, a sound wave, an earthquake wave, that's wave on a stringed instrument. So many of the same rules, the same concepts are universal for waves. Okay, and as a thing to note is that frequency and wavelength are inversely proportional. So as frequency goes up, wavelength goes down. And that's especially true of light because you can't change the velocity. The speed is fixed. So that means that if you're, as I said before, if you know one, you know the other. If you know the wavelength, you know the frequency. And you also have that same inverse relationship. As the frequency gets bigger and bigger, the wavelength gets shorter and shorter. So that's a general rule. And so when you look at light and you talk about all the different types of light, you really you can it's almost like you can choose how you want to consider it. Do you want to consider the range of frequencies, or do you want to consider the range of wavelengths? And those two different choices of how to conceptualize light are chosen because of different situations. One is more appropriate for a certain question than another. But you got to remember that they tell you opposite things in that, the ends of the spectrum are going to be big and, small and big for frequency and big and small for wavelength, which is probably hard to visualize, but you will see it in just a minute. So, quick concept question for you. The radio station KKNX emits radio waves with a frequency of 840,000 hertz. Remember, hertz is how we measure frequency. KLCC emits radio waves with a frequency of 89,000 or 89,700,000 hertz. Which station emits waves with a longer wavelength? So here you're given two different frequencies. One's obviously bigger than the other, but which one has the longer wavelength? Okay. All right. Thumbs up. The KKNX, the one with the lower frequency. So you're remembering the inverse relationship? Well, if you are, you're right. That's exactly it. So the one with the lower frequency has the longer wavelength. And you could use bigger and smaller in both cases, but we tend to say high, low for frequency and short, long for wavelength. But big, small could be used for both of them, just not entirely, like totally correct English, but would get the point across just fine. But the important thing is that as one goes up, the other goes down. Frequency goes up, wavelength goes down. Inverse proportional. Okay. So a frequency for the if you have a slow wiggling, so that would be like low frequency, wiggling being, another term for a oscillation. I find that a lot of students don't know that term oscillation. It literally just means wiggle. It's what waves do. They oscillate, they go back and forth. So low frequency, slow wiggling, which would correspond to long distance, so long wavelength. But if it's fast wiggling, short distance, right? Compact wavelength, short wavelength. All right. That's the rule. That's the trend. Right. So now let's categorize light based on its wavelength. I said we could do it either way. We could categorize light based on wavelength or frequency, but we will start with categorizing light with wavelength, which is the more common way to split light into its different types. Okay, so let's look at our very long waves. So the longest wavelength waves of light are radio waves. And these are going to be waves that have wavelengths that are greater than 10 to the 9 nanometers. Well, what is 10 to the 9 nanometers? Well, it's actually just 1 meter. So that's what we're talking about when we talk about radio waves. We're talking about waves that have wavelengths that are 1 meter or longer. So, we got car keys, FM radios, AM radios, submarine communications are some of the longest ones that are used. There are natural phenomenon that produce radio waves as well. There's a number of different types of astronomical events and objects that create radio waves. Really cold nebula create radio waves, as do really like really hot stars, but for different reasons. So you can have these things called radio galaxies that have actually where the radio waves are created by the ejecta from supermassive black holes, or the which obviously black holes don't eject things, but the things that accelerate and don't quite reach go into the black hole. They have these big plumes that come off from the sides of them. So there's these different ways that radio waves are made in space, and obviously humans also have taken advantage of radio waves, and we create them for our own communications, right? And so, some of the search for extraterrestrials has involved a search for radio waves, because we've long assumed that another alien civilization might use radio waves the way we do, and maybe we could detect them, because many of our radio waves also get transmitted out of the atmosphere, sometimes on purpose, sometimes accidentally, and they would travel out into space and could be detected by aliens. But we haven't heard anything, and no one has reached out to us. All right. But those are our longest wavelength forms of light. This is the type of light that people, I guess, would most commonly forget about or don't think of as light. It's kind of weird to think about radio waves as light, because it's certainly invisible. It's much lower energy than visible light, but it's the same form of energy. It's just longer wavelength. Okay. Well, as we get into shorter wavelength light, we move into the part of the spectrum. Notice the title up here, electromagnetic spectrum. That's what we're talking about, which is just a name for all the types of light. So we move into microwaves. The microwaves have wavelengths that range from 10 to the 6, which would be a million, up to 10 to the 9 nanometers. So in other words, they range from a millimeter to a meter. All right. So microwaves can be a centimeter long, for example. That'd be kind of right in the middle. Microwave ovens are an example. They have a, a length that is a few centimeters long, like around like 4 centimeters, and it's really good at cooking food because of its particular relationship to the water molecule and its ability to make water molecules vibrate. Other examples, cell phone, Bluetooth, those all use microwaves. Essentially, microwaves are called micro because they're short radio waves. So the micro refers to that they're basically still a type of radio wave, and that's how people have thought about them for decades. But they're the micro version of them. Yeah, so that's why they're called microwaves, can be a confusing name because they're actually they're the second longest type. So why are they micro, right? Well, because they're micro radio. Okay, so continue on. Okay, well, before we do, microwaves have a shorter wavelength than radio waves. Do radio waves or microwaves have more energy? So, which carries more energy? Radio waves like AM, FM, or microwaves? What do you think? Or what do you know? Okay, gonna vote for microwaves. A questioning vote for microwaves. Okay, but it seems like yeah, it's winning out. Everyone thinks microwaves. Almost everybody. Okay, let's see. Moment of truth. Sure enough, microwaves carry more energy. They might just seem that way because you think, well, if they can cook food, I've never heard of an FM radio being able to cook food. So that might be one way to think about it. Although that could be misleading because the way that microwaves cook food is more of being like fine-tuned to water than anything else. But the main idea, and I'm sure many of you thought about this, is just the inverse proportionality between wavelength and frequency. So we just have that the frequency is proportional to 1 over the wavelength and is directly proportional to the energy. These are both things that we've seen in the slides, but I'm just summarizing them a little bit differently than we have seen them. Okay, so we have a inverse proportionality between frequency and wavelength, and we have a direct proportionality between frequency and E, where E represents energy. So therefore, if you have shorter wavelength, you have bigger frequency. And if you have bigger frequency, you've got bigger energy. That's the way to see it. All right. So do something real fast. All right. Short wavelength, high frequency, high energy. I didn't mean to write over it. Okay. So far we've talked about radio waves and microwaves. What's next? Well, infrared. As we get short, we're moving from longest wavelength to shortest. Next up, infrared. All right, so the whole category is called infrared. The main types of light that are within that category are like TV remote controls. So it's used for like a lot of sensors use infrared and heat. So like the typical kind of molecular vibration at kind of like Earth surface temperatures is going to cause a type of spectrum that's peaking in the infrared. So what I mean by that is everything around you is glowing. It's all glowing with heat. In what you don't see it. Instead, you're seeing all the reflected light that's coming off of objects. In some cases, you're seeing emitted light if you look at like an LED or a screen or a light bulb. So you're seeing an emission of light. But mostly when you look at objects around you right now, if you just kind of turn and look at your room that surrounds you, you're seeing reflected light. The color of your shirt, the color of the table, the walls, that's all just reflected light. If you could see in the infrared, you would see a lot more emitted light. Because then not just the computer screen and the light bulbs and things and a few LEDs would be emitting light, but everything would be emitting light. Because like I said, everything is glowing. It's just that we can't see it. Our eyes can't see infrared. They just not evolved to see them. And even if they could, that light would be a lot dimmer. The infrared light would be significantly dimmer than the reflected light. So we would have to probably be in a dark room to see it in the first place, even if our eyes were capable of seeing infrared, which they're not. Some animals do have eyes that can see infrared. It's not unknown in the animal kingdom. All right. But that's what we mean by heat being infrared. What's interesting is that when we talk about objects in space, we have lots of objects that are much colder than a typical object on the surface of Earth, and other objects that are just naturally hotter. So we have cases where things are glowing, in the same from this based on the same principle that we glow, which is just molecular vibration, but it's either glowing in the radio waves because it's really cold, or it's glowing and it's hot enough for us to see. But of course, we already know that we can heat things up and make them visible. When you take a piece of metal and you hold it in a flame and it becomes red hot, that's a perfect example of heat going from the infrared and moving into the visible. So we're like we would be taking this pyramid here, this peak for heat, which kind of just represents the most common frequencies or wavelengths, in this case, of heat. And but if we take a typical object and we warm it up, we'd move that heat signature into the visible. And that's literally when things start to glow red hot, which is the perfect transition to the visible spectrum. So the visible spectrum bordering the infrared, all right, on the long wavelength side is shown right here. And it's tiny, right? It's just a really, really small section. It covers a much smaller range of wavelengths than the three types of light we've talked about so far: radio, microwaves, and IR or infrared. It's just the particular, light that we've evolved to see, which is not coincidentally the light that passes through Earth's atmosphere most easily. So it's the most abundant range of light. It's a fairly tight band just because of the particular properties of our atmosphere and our sun, And so that was the light that was available. So it's the light that most animals evolved to see. And that's just the particular case. It could be a broader range, certainly. And as I said, some animals do see a broader range because of a certain, criteria that is advantageous to them to see other types of light. And you could imagine other worlds where there's a broader range of light, but not that much broader in terms of like kind of just like the peak light. It's always going to be a fairly narrow range, but it's just part of a bigger story. All right. And I didn't mention values for the infrared. I wanted to quickly get back to that. That the infrared varies from 1,000,000 nanometers down to about 1,000 nanometers, and it really is almost 1,000. So that begs the question: what's the range for this little band for visible light? Well, the little band of visible light, we'll come back to it, but it's gonna vary from about 400. I should have used a purple pen. And that's on the violet edge. So that's the shorter wavelength edge of visible light. And I really wanted to do this because this is literally why we're talking about this whole scale of nanometers, is because nanometers is so well suited to visible light, because it means that everything is going to be in the hundreds, which just works out nicely. You don't have to worry about decimals. And then red is about 800. And these are estimates. There's really, you could be a little more accurate, but this is kind of a rough estimate of the upper range in terms of wavelength and the lower range of the rainbow, right? But also the visible light spectrum or portion of the spectrum. All right, now we keep moving to shorter wavelengths and we get into higher energies, which is, so it's no surprise that we see the word harmful come up, right? So harmful sunlight is ultraviolet. Ultraviolet itself is the whole category of light that is shorter wavelength, higher frequency than visible light. So visible light is, has boundaries on either end of ultraviolet and infrared. So if you go past red, you get infrared. If you go past violet, you get ultraviolet. Right? Names make sense. Okay. Black lights are kind of the far end of ultraviolet. So they have the longest wavelength and the lowest energy, because we don't want black lights to be the really high energy type of ultraviolet, but they're just barely invisible. They're great for causing particular types of triggered emission. That's where you get the what's called fluorescence, which is you have something glow that otherwise wouldn't glow. And it's interesting too, because a lot of rocks are fluorescent, and different types of sea animals. So it's a surprisingly widespread property of different molecules, biological and otherwise. Okay, so let's wrap up the spectrum here. We got X-rays next, even shorter wavelength and even higher energy. So X-rays are so high energy that they can penetrate skin, and they only reflect off of things like bones and other really high density biological matter, but they easily pass through tissue and most organs. Okay. They are created in all types of astronomical phenomenon, so they're pretty common in astronomy. And there are lots of telescopes that are specifically X-ray telescopes. So I haven't mentioned this, but so much of these different spectra that we're talking about are viewed by astronomers. Many, many telescopes are not visible light telescopes, which, of course, and this is a good time to mention it, of course, that makes sense because look, visible light is this tiny little slice of all the light that's out there. So if you want to explore the universe and you want to look at all the different light that can be created by everything from black holes to stars to nebulas to galactic collisions and all these different phenomenon, well, you want to look at everything. And all these different types of light can be created and are created throughout the universe. So there are specialized telescopes for each type. So X-ray telescopes are no exception. And then finally, there's gamma rays. Gamma rays are the shortest wavelength, highest energy light. They are rightfully associated with nuclear phenomenon because they have very high potential energies associated with the states of the nucleus can lead to gamma rays. There are actually some electron transitions that can lead to gamma rays, but mostly those lead to X-rays. And so gamma rays almost exclusively come from the nucleus of atoms, because that's the only place where enough energy is held in order to produce them, which is kind of an interesting thing. It's just which we'll touch on. All right. So getting back to the visible, right, the small portion that we see, bounded by ultraviolet. Okay. And check our time. Let's see. Yeah, so let's get into thermal radiation a little bit. Back, okay, nothing in the chat before we take our break. Find this. All right. So I mentioned thermal radiation. This is a key way that astronomers use light to gain information. Okay. So radiation is a term for light. I That's not widely known. People think about radiation, they think about, well, actually something we just mentioned, which is nuclear radiation. And that's fair. I think sort of scientific names have sort of done a bad job of separating what radiation is. When we talk about radiation from like nuclear processes, so nuclear radiation, there's three types. One of them is gamma rays, which would be light. The other two types are actual particles, either electrons or these things called alpha particles, which are a the nucleus of a helium atom, so just two protons and two neutrons and no electrons. So those things are readily emitted from the nuclei of large elements like uranium and plutonium, and also sometimes lighter elements. But the point is that two of them are just particles, and one of them is light, and they're called radiation because they were thought to all be light originally, and so radiation was kind of always intended to be a term that just meant light, and it's still widely used in the discussion of light to refer to it. So it's sort of it definitely confuses the general public though that we've got nuclear radiation, which mostly isn't light, although it can be with gamma rays. And then we got, the way it's used in scientific books and so on, where it's referring to light in general. So just take note of that. Not ideal naming, but when we talk about light, we're talking about radiation and vice versa. And specifically here, we talk about this thing called black body radiation. And this is always the name given to the the rules for thermal radiation. So you can think of thermal radiation as being kind of the more less technical name for what we're talking about, and black body radiation being the technical definition, the technical name. But why black body? What the heck is that? Well, it's just referring to something where it's has low reflectivity, so it's not like a metal, and when it heats up, it starts to glow based on its temperature. So interestingly, a human would be a black body. Our surface is not highly reflective. And as we warm up, we glow at higher, shorter and shorter wavelength, higher and higher frequency. We glow with that light with that property. A star is another black body because again, low reflectivity. As the star heats up, it glows at different different frequencies based on its temperature. And so is a planet, a rock is a black body. So it's basically any solid object that isn't very reflective. um I keep mentioning reflectivity as being a property that a black body has to not have. So metals are not good examples of black bodies, like a slab of metal, for example, or aluminum foil or something. The other case, the other substance that would not be a black body would be any gas. So gases do not have a clear relationship between temperature and color being a stand-in for wavelength. So because obviously, red has a particular wavelength. So when I say, the color, I'm referring to the wavelength. And same for blue and green and so on. So gases, and that would include gases in space, like nebula, do not follow the rules that we're about to talk about. But planets, stars, rocks do. Okay. So, here we have something heating up. We've got, and I think, oh, well, this is like a metal coil that's heating up and going red. But if you think about the heating element on like a old-fashioned electric stove like this, it's like black and sooty looking, right? So it actually is, it meets that black body criteria. All right. Cold in a fire would also be a black body. So these are kind of terrestrial examples of black bodies. The different colors correspond to different temperatures. Okay. So here's a picture of an actual radiator. So black bodies emit some light at all frequencies, and that's called the black body spectrum. So we'll see it's a curve, and all the frequencies actually exist, and that's because there's always a certain chance of the molecules within this solid object vibrating in any way. But the chance becomes really small outside of a certain range. And so we have a frequency curve. So what I mean by that is like, so take a look at this curve, okay? So this would be the black body spectrum for a particular object. In this case, a burner with a temperature of 1200 degrees Fahrenheit, which is equivalent to 649 degrees Celsius, or the temperature scale that we'll use almost exclusively, the Kelvin scale, which is, so this temperature would be 922 Kelvin. So we might refer to these other temperature scales, Fahrenheit, maybe a little bit of Celsius, but really we're working almost exclusively in the Kelvin scale. If you haven't seen Kelvin before, we'll kind of touch on it a little bit just now. But I think it'd be best to review it and just check out that it's what's called an absolute temperature scale. And that's why it's so widely used in astronomy. And so, in other words, absolute zero is 0 Kelvin, and that's a real good like clarity. It's the best scale to use when you have such a huge range. Because in astronomy, we have things that are nearly absolute zero, and we also talk about some of the hottest things you could ever imagine. So astronomy covers the full range of temperatures. But getting back to our burner here, that's glowing red hot, so producing some visible light. It's got this curve. So this would be the curve of its energy output. Notice the vertical axis. So the vertical axis just represents how much energy is being produced. So the peak of the curve tells me that the most of the energy, the peak energy, is being produced right here. So then what you do is you look at the peak, and then you draw a line down from the peak, a vertical line, and you just see where that intercepts the horizontal axis. And that would tell you the peak wavelength. So you look at the peak energy output, which can also be described as the most probable energy output. So this is where most of the molecules that are making up the black body are vibrating, and what type of energy they're producing. And so that most probable output, the peak energy, is happening at a wavelength of between 4 and 5,000 nanometers. So invisible, infrared, right? So that's where most of the energy is being produced. But we can see the burner, remember? The burner is visible. So why is that? Well, because there's a little tail on this energy curve on the black body spectrum, and all the black body spectrums look like this. They're all this like the if you've seen like these types of curves in a stat class, then they might look familiar. They're related to the so-called bell curve, which is the distribution. But in the case of black body spectrums, they're always skewed like this, so they're always lopsided. But the point is that they're that type of curve. They're a distribution. But if you look down here, there's a little bit, what we call a tail, that goes into the visible spectrum. So it's a tiny portion of the overall energy that's being produced by the burner, but it's enough to make it visible. So if you think about it, like if you could see the infrared, you'd be able to see way more, and potentially it'd be brighter depending on how receptive your eyes are to infrared. But of course, our eyes are not able to see it. So we're stuck only seeing this little tiny fraction of the energy that's being outputted. Sometimes that's brought up as an example of why old-fashioned light bulbs, like tungsten, uh, I want to say iridescent, but that's the wrong word. But tungsten light bulbs that would just produce light by having a little glowing filament. They're always described as being terribly inefficient, and they were, because most of the light that was being produced was actually heat, which is why light bulbs were always so hot, and you had to be careful. Now that we've switched over to fluorescence and LEDs, we've really been able to improve the efficiency, because now we're producing we have a light bulb where most of its energy is going into visible light, which is the desired outcome. Unless you want to have a heating light bulb, like for a lizard or something, well, then you want to use a different type, right? Or you just want to use a heater. So, but we often got heating as a unintentional and sometimes undesired, byproduct of light. We've improved upon that, right? And that's related to this type of curve. All right. So check the time again. Let's see. Let me look at something real fast. Incandescent. Thank you. The word is on the tip of my tongue, but it once iridescent got stuck in there, I'm like, oh, I'm not going to think of it. So, but thank you. Incandescent. That's the type of light bulb I was talking about, which now are old-fashioned, outdated, and replaced almost completely, but not worldwide, but certainly in the United States. Now just let me check something real fast. Oh, I think I'm not sharing anymore. Sorry. Okay. Yeah. So I want to take a break before we would be able to finish the black body section. So with that in mind, let's wrap things up for our break. Okay. So quick summary here of different or the different portions of light that are produced for a 1200 Kelvin glowing object. If you take a 1200 Kelvin object, this is like the portion that falls into the different categories of light. So a tiny fraction of the light is radio waves, and that's like the tail over here. Tiny portion is radio waves. Very small portion in the microwaves. The vast majority would be infrared. So in other words, this curve is pretty solidly an infrared curve, with like a little bit bleeding into visible and, maybe you could say a little bit bleeding into microwaves. If you were to look at other temperature objects, you can make other similar curves. And I'll just do one more before we wrap up for our break. So you look at something that is glowing like a incandescent light bulb and the filament. Well, that's going to glow at a temperature that's about twice as hot as the burner. So we have 1900 Kelvin, almost 2000 Kelvin. And we have a much bigger section in the visible now, right? So it's the peak is not in the visible spectrum. The peak is still in infrared, which is again kind of strange considering that the primary use was to create visible light, right? But they did their best. And right, and then if we keep going, look, we can get to the sun. We'll check out the sun. Look where the sun's peak is, right in the middle of the visible spectrum. Man, whoever made the sun really made it good. They made it so it matched humans. But of course, as I said before, it's the other way around. We evolved to match the light that was there. So the sun, right, has its peak right in the middle of the visible spectrum, literally kind of right at green, which is smack dab in the middle of the Roy G bid, red, orange, yellow, blue, indigo, violet. Okay. ROY, green, G, BIV, blue, indigo, violet. Okay. And the temperature that gets that peak right in the middle of the visible spectrum is a temperature of 5,800 Kelvin. So 5,800 Kelvin is the surface temperature of the sun. And that the surface temperature is what we care about for the visibility, because that's what we see. We see the surface of the sun. The interior of the sun is much hotter, but that doesn't relate to what we're seeing. So we see its glowing surface. It is a black body. The light it produces is a black body spectrum. It has that curve shape to it, and it has both UV and infrared portions as well, but peak in the visible. All right. A hot source emitting black body radiation. That's definitely what the sun represents. All right, so we'll leave it there because we'll talk about splitting light into its components, how we can take, a spectrum like this, which is called a continuous spectrum, by the way. It's just another term, although it's a interchangeable term with black body. And we can talk about how we can split it into components. Okay. Oh, a bunch of messages just now. Appointment soon is okay. Yeah, you're absolutely leave early. I will be posting the recording. I haven't posted yesterday's yet, but I'll get on posting. both yesterday's and today's recording if you want to kind of see where you left off. It'd be a good idea just to wrap things up. You could always watch it on double speed, so it takes less time. And we have a quiz in the sense to answer Zanab's question, but it's on Canvas. This is our first Canvas-based quiz, which we'll be doing occasionally. We will have an in-class quiz tomorrow on the content that we are covering right now. So we got one coming up. Cool. All right. So I'm going to pause the recording from now and take a 5-minute break. 5, 6 minutes. I'll be back at 11:25. I'll see you all then. All right. Now continuing with chapter 5, talking about black body radiation, which is also known as thermal radiation. It's the way that we can look at the color of something and know its temperature. We haven't spelled out that relationship explicitly, but we will in just a moment. Okay, so to talk about splitting the light into its components, we want to consider a prism. As you might know from just an experiment in school, if you take white light and you shine it through a prism, you can split that white light into its individual colors. So white light is specifically what we see as white light is all of the visible wavelengths of light. So split into a full rainbow. And that's the case of light coming from the sun. The sun is the definition of full spectrum, rainbow producing light. All right, so that type of spectrum, continuous spectrum. And that term will be used in contrast to absorption spectrums and emission spectrums, which we'll talk about in a minute. Okay, now I've hinted at and mentioned many times that temperature relationship. So we've got this type of spectrum, black body radiation, which is also called thermal radiation, which is also called a continuous spectrum. So few names for the same thing. And some of those names are, used in different contexts, right? Okay, but how is this whole type of light that's produced from the sun, for example, directly related to temperature? Well, there is a clear relationship where you look at that peak and you can relate that peak to the temperature. And we have a formula to do it, which you'll be seeing in the homework, and it's called Wien's law, and it's a simple formula that lets us relate the peak wavelength that's produced in one of these curves, one of these black body spectrums, continuous spectrums. So relate that peak wavelength to the temperature of the black body. Okay, so now to make sure that this idea of peak wavelength and curves make sense, which temperature peak is at red light? The 7500 Kelvin peak or the 4285 Kelvin peak? And notice that it's referring to one of the curves. So one of these curves is the 7500 and the other curve is the 42, but which is which, right? They're not labeled, but you can know which is which if you kind of think about the trend that we saw when we talked about the other types of glowing objects a minute ago. Okay, so I got a vote for the 7500 having the peak at the red light. Everyone agree? Which temperature peaks at red light? The slightly cooler 4285 Kelvin or the hotter 7500 Kelvin? I've gotten one vote so far. Let's get a couple more. All right, I got a vote for the 75. Okay, let's see the answer. It's actually the 4285. And it's tough. I could totally see how you could, think that. And we saw the sun, right? What was the sun? The sun was 6008, no, 5008. Yeah. And 5008 was right in the middle of the visible. So we know that so think about it this way. We know, and this is without even the formula, just kind of piecing together information, examples. We know that a object that has a temperature of 5,800 Kelvin has a peak at green. And yes, that does mean that the sun is green, but of course, it doesn't look green, it looks white, right? And then it looks yellow when we look at it through the atmosphere. But if you see it in space, it looks white. The reason it looks white is because it's got just as much, of the colors, you know, to one side of green as it does to the other side of green. But the peak is actually at green, right? But it doesn't appear green. So anyway, so if you have 5,800 has a peak right at that section, right in the middle, right? So the sun's peak would be right here. Well, then we can say, okay, if I move in this direction, that has to be colder than 5,800 in order to have a peak at red. And the answer that's colder than 5,800 is the 4,285. So we know that would be the temperature of the object that has a peak at red. Whereas the object that has a peak at blue is the 7,500 because it's hotter than the sun. It's hot enough to glow blue, right? And it would actually appear blue, although not pure blue, because the other colors would contribute to it. So it'd be like a sort of like a blue color with whatever you get when you mix in a little bit of the other colors of the spectrum, darker blue essentially. Um, but the point being is that its peak would be at blue. Okay, maybe I have a question about that. So with this graph, the height is descending while moving right. Um, height is descending. They all the curves fall off. So they're the blue curve, black body spectrum curve, and the red are separate objects. And then the heat is yeah. Yeah, okay, I see what you're saying. Yep. So exactly. So the heat of the object is yep. So the trend is that as the peak moves in this direction, the temperature moves down. Yep. So as the peak of the curve moves to the right, the temperature decreases. That is correct. Yep. Yep. So peaks further to the right correspond to cooler objects. Peaks further to the left, like the 7,500 Kelvin object, correspond to hotter objects. Absolutely right. Right. Moving on. High temperature, peak closer to blue. Low temperature, peak closer to red. And you can have peaks outside of blue and red as well, right? So you could, saying closer doesn't always apply because sometimes it's beyond red or beyond blue. There are plenty of objects that are so hot that their peak is well into the ultraviolet. All right. And as I've already mentioned, the peak wavelength is not the color because the actual color is the combination. So often, it's just that that what you see is you have to think about how it's going to look, which sometimes is obvious with the sun because the peak is right in the middle of the rainbow, so that because of that symmetry we can say that it looks white. But then in other cases you got to think about it more carefully, and it's not immediately obvious, but I wouldn't ask you something that'd be tricky. But the important thing is that the stellar color reveals its temperature. So this is a powerful tool that astronomers have. If they can look at the color of a star, they know its temperature, which is incredibly valuable. And we'll come back to this idea because it's a crucial part of the way that stars are categorized is based on their temperature. And the fact that we can do that by just looking at the color is a wonderful simplicity, really, in terms of like it's a pretty easy measurement to make just to find the color of something. Even though stars are just little specks, to take that little dot and split and be able to analyze it into its individual wavelengths is easily done. All right. So when we look at the sun, the amount of red, green, and red light gives the color. Right. So we end up with the color of the sun. And This view of the sun where it looks, looks kind of red is more of just like a filtering effect of what we're actually seeing in this image. In fact, a lot of times when you see these images of the sun, like the one that's showing, it's actually not a true color image at all. It's often, and I think this is actually an example of it, it's an X-ray image that has been artificially colored because X-ray emission shows a lot more of the interesting things like the big plumes and the coronal mass ejections and the all the stuff that's going on the surface more clearly than the visible spectrum does. All right. So temperature and the major light type radiated are can be directly related to the spectrum like this. So we could actually look at the electromagnetic spectrum and split it into temperature ranges. So far we've looked at the electromagnetic spectrum and the seven types of light. See? And we've really just seen it as splitting it up into wavelength categories, but here we're splitting it up into temperature categories. So something that emits gamma rays through black body radiation is going to be have a temperature that's over 180 million Kelvin. So, which is a difficult feat. Most things don't exist at 180 million Kelvin. You've have, you know, all these different, obviously, you go through all these phases, right? And you get to, you know, a plasma, which is this, like condensed gas that's, as hot as you can get. But then as you continue to heat things up, you start, overcoming the electron energies. So that's why it becomes a plasma as opposed to a gas, because you've ejected all the electra. And if you continue to heat something up, you overcome the nuclear binding energies and you start breaking things down into simpler elements. So in order for something to actually be glowing gamma, it wouldn't really be exposed to space. There might be some objects. I don't know off the top of my head about some, certain pulsars or maybe some of the rims around black holes, but it's not common. We'll say that much at least. There are some examples of those extreme phenomenon like the hottest dead stars and black hole accretion disks that actually are so hot that they glow in the X-ray spectrum. So their peak wavelength is in X-rays. UV, you can see anything that has a surface temperature between 1,800,000 Kelvin and 17,500 Kelvin would be glowing with a peak wavelength that's UV. Well, the upper end is pretty extreme, but the lower end falls into certain types of stars. So the very hottest stars, which are these relatively short-lived, very massive stars, actually have surface temperatures that are around 20,000 Kelvin. So that would be a star where its peak wavelength is UV. Obviously, visible spectrum would be things like our own star, and then we can continue in other temperature ranges with infrared being a range between 1,340 Kelvin and negative 440. You have to be colder than negative 440 in order to be glowing microwaves. So those are very cold objects in terms of the temperature. And I was thinking, wait, that can't be Kelvin, and it's not. This temperature scale is Fahrenheit. There is no negative for Kelvin. So what's interesting is that although it's kind of a pain that this temperature scale is Fahrenheit, it doesn't matter so much for the big numbers because the offset between, Fahrenheit and Kelvin is just a few hundred. So it's not going to matter when you're talking about millions. But here, I think they chose Fahrenheit just so it'd be more easily relatable. But negative 440 is approaching absolute zero, although not quite there. And you can get colder. You can get down to things that are actually glowing well into the microwaves. Human temperature at 98 Fahrenheit would be solidly in the infrared, which is the one distinct advantage of using this temperature scale. We know that our surface temperature 98 degrees. Well, that means that we glow infrared. We are a black body that glows infrared. Okay. So there's the sun in Fahrenheit, 9,941. Okay. Earth. So the average surface temperature of Earth is 60 degrees Fahrenheit. So the planet is glowing. If you could see Earth with infrared goggles or some sort of infrared detection device, you would see it glowing in the infrared spectrum based off of its temperature. Interstellar gases. are less than negative 441 degrees Fahrenheit. So they're going to glow in the microwave or radio wave spectrum. They have these really cold nebula that glow at that really low temperature. What's interesting is that sometimes the distinct signal that comes from those really cold nebula isn't even their black body spectrum. It's other types of emissions that they create, but they do have a steady faint glow that in the microwave or radio wave. In fact, and touching on the other things that can happen from types of spectra, let's get into more about gases. Okay, and actually, it's kind of funny that we talked. I said that gases aren't black bodies, and I kind of contradicted myself right just now by accident. Really, when we talk about some sort of black body emission coming from a nebula, it's it's not ideal, and sometimes it's really most accurately used for one that has a heavy dust content, because then you can say that like all the individual pieces of like kind of micron sized but not nano sized chunks of dust are behaving like a black body, and that's the signal that you're picking up. But for like an atomic gas or purely molecular gas, there really isn't the right physics to lead to black body radiation. Because just to touch on the idea without it being something you're accountable for, you have to have this like huge range of possible vibrations, and you don't get that when you have like a purely atomic substance. Then you have just a few possible vibrations and not enough to create that curve. Instead, you have a few peaks, which is something we'll touch on right now. Okay, so going to gases. If you have a very cold gas, okay, well, a cold gas can absorb light that passes through it. So we're gonna talk about gases absorbing light. So this gas is out in space, and maybe there's a star behind it, and the light from that star is passing through the gas, and some of that light from the star is getting absorbed by the gas. What does that mean? Well, cool gases absorb only specific wavelengths of light depending on their chemical composition. Okay, so this is why it's not behaving like a black body, where there's so many different combinations of chemicals and different ways that object can interact with light and electrons and electromagnetic waves. Okay, instead, with a pure gas with a very simple composition, there's just a few distinct ways that those molecules can vibrate, or the atoms can excite. Those are two different things that can happen. Molecules can vibrate, and they can vibrate in a couple of different ways, kind of like springs or like spinning tops. But then electrons and atoms are different. Atoms can only have their electrons go to different shells of excitation, and that's how they can absorb or emit light. So if we have incoming light, in this case, violet light, so fairly short wavelength, high energy light, it's going to come from the vacuum of space and approach our gas here, our low density gas, not a black body, right? Last time I'll say that, I promise. And the light's going to come in, right? And in this case, with the violet light, pass right through. Well, in this example, that's because none of the molecules, which are shown as the little kind of dumbbell shaped, bar shaped things, or the atoms, which are shown as the typical atomic symbol, none of these either atomic substances or molecular substances that compose our gas, our nebula, our space gas, are susceptible to violet light, which is why it passed right through. And susceptible is a general word. The technical term would be none of the excitation levels of the molecules or atoms match the energy carried by the violet light. The violet light carries a very particular amount of energy, which is directly related to its frequency. As we said, well, only atoms or molecules that can absorb that exact amount of energy will respond to that type of light. So if no such molecules or atoms exist, the violet light just passes through as if the gas wasn't there. But if we take orange light, now in this example, the molecule is able to respond to orange light. because of its particular composition, because of what molecule it is, it just has that ability. And it would depend on the exact wavelength of orange light, right? A slightly different wavelength wouldn't have the same response. When you get in the molecules, you end up having so many different closely packed excitation levels, as they're called, that often it's like a whole range of orange light because you have all these different possible states. With atoms, especially simple atoms, often it's just very widely spaced particular colors that can respond, and that's it. And the smaller the atomic nucleus, the more distinct and separated the absorption bands are, which are just the possible colors that can be absorbed. So we see that most of the orange light was absorbed by the gas. Okay, so it didn't pass through unimpeded. So then if we think of a continuous spectrum, so the type of rainbow light, continuous light that's produced by a black body like a star, well, when that comes through, we've got, what was it, orange being absorbed and blue. So, see, we hadn't seen it yet, but it turns out that the atoms that compose this gas are able to be excited by blue light, which means they absorb it. So there you go. So all that passed through was the red, yellow, green, and violet, and we lost our blue and orange. Okay, so white light entered, full bandwidth, continuous spectrum, and the dark lines, those are the missing colors. So the dark line would be the missing orange and the missing blue were absorbed, and we call those absorption lines. They're removed from a continuous spectrum. So we have our continuous spectrum, which didn't have any missing sections. And when we put a cool gas between the source of that continuous spectrum and our observational prism, we now can observe these dark bands, which are called absorption lines. And what do they tell us? They tell us about the composition of the gas. All right, so the absorption lines appear in the absorption spectra as dips in the intensity. So what they, on an analysis, on a digital analysis, you would have, these curves and you have these clear dips. All right. So we have the continuous spectrum, and this is on a graph like we've seen before, the same one where we identified the different temperature objects based on their curves. So vertical axis being energy output, and then horizontal axis being wavelength. So we have a continuous spectrum, then we have the gas. And so the dips are the absorption lines. So for analysis, this is what they would look like. Although in a simple analysis, if you just wanted to look at the projection onto a screen, it could look like this, where you just see the bands. But if you want to look at exactly at how much absorption there is to actually quantify it, then you would look at this graph and you'd see the dips. Okay, so picture version, graphical representation, but same thing. Absorption spectra because of a cool gas, right? And a different gas would have different absorption lines because of the different composition of molecules and atoms. All right. And then we have which source is hotter. And that would be the source of what? I guess the black body source. We'll skip this one for now. But I think it is referring to not the gas, because the absorption lines don't tell us about the gas. Yeah, yep. So it was referring to the background continuous curve and essentially ignoring the absorption lines, which is funny because we're talking about absorption lines, but you got to follow the directions, and it asked you about the source, and the source of the light is not the gas. Okay, the gas is just in the way. But what's cool is, again, that despite that, the gas just being in the way, as I said, the absorption lines are crucial for us identifying what the gas is. So they're a very useful tool. All right. So we see those drops in intensity, and the absorbed light gets re-emitted. All right. So now we're going to get into how gases also have emission lines. So the difference between the two is often just orientation. And that's crucial with astronomy because everywhere we look, we've got our line of sight, and we can't change that very much other than our small variation throughout the year. And you might think, wait, it's not that small. We orbit the sun at a distance of 150 million kilometers, right? That's a pretty big distance. But compared to, stellar distances, it's tiny. So we're almost like fixed, we have our fixed viewing point. And sometimes when we look at certain parts of the galaxy, we've got a gas between us and a star. Other times we don't. Instead, we just have a gas and there's no, star right behind it. So it all kind of depends on what our view is. So if we had a clear view and where we could tell there was a star behind a nebula, and we could really clearly see the light passing through, we'd just be seeing the absorption lines, at least primarily. But if things were skewed a little bit and the light was hitting the gas from the side, and then we had a clear line of sight to the gas, we'd actually be seeing the light that gets re-emitted by the gas. And you may have been wondering about this because we talked about the light being absorbed that passed through, right? Well, where does that energy go? Does that energy just get trapped inside the gas forever? No, of course not. It eventually gets re-emitted because that's the way these energy phenomenon interact. We have energy changing from one form to another, changing from electromagnetic to the potential energy of the molecules or the electrons around the nucleus of the atom, and eventually, just because of various spontaneous interactions, that energy gets released. Sometimes it actually can get in certain cases, certain atoms and certain molecules that can get held for a very long time and just sort of like get trapped in there. That's why we have things that are phosphorescent, things that can glow for a long time because they hold on to the energy and then slowly release it. Some gases are the same way, but usually they're going to release it pretty darn quickly. There's a very, very small time scale of the probability of that energy staying in the excited electron or the excited molecule. The chance of it relaxing back down to what's called its ground state is a very high chance, and that's a kind of a universal rule in physics. So, what happens when these molecules and atoms relax? They emit the light, and they emit it in a random direction. There's no correlation between the direction that the light was absorbed and the direction that it was emitted. All right. And so that means that the gas is glowing in every direction, not glowing from black body radiation, but glowing from specific vibrations at the molecular and atomic level. Right, so here we have the atom also releasing. We just saw the molecule the first time. Here's a case of the atom and molecule releasing light in a particular direction, making its way to our observer with their observational prism, splitting that light up. And what do they get? Well, they get a spectrum that's mostly just blank because there's no continuous spectrum here. There's just the emission from these very specific phenomenon that are, as I said a while back, the fingerprint, so to speak, of the atom and the molecule, because they're very specific to that particular molecule or atom. And they just show up like this, just a band of color and otherwise blank for our spectrum. And that type of spectrum is called an emission spectrum. So at this point, we have seen all three types of spectrum that we will discuss, spectra that we will discuss the entire summer. We've got continuous spectra produced by black bodies. We've got absorption spectra produced by gases that are absorbing light. And we've got emission spectra produced by gases that are emitting light. When we look at the graph, energy output per wavelength, the emission lines show up as peaks with some sort of background, which isn't quite zero just because of either noise in the system, which means it's like random variation, or because of something else that's going on, but that is not as strong. So as I said, line of sight is crucial. So astronomers on two different planets look at a cloud of gas in space that is near a star, right? So presumably one of these astronomers is an alien. Which astronomer sees an emission spectrum? Okay, so let's go ahead and answer this one. I'll source you for answers. Okay. And real fast, I see a question that Sarah dropped into chat just a minute ago. You can't see the assignment that is due today. It's just the quiz 4. You should be able to see it, but I'll double check. So quiz four is due today, and so is homework two. But quiz four was the one that I was referring to a bit more. But you have two assignments due today. So let me know if that invisibility persists, but hopefully they show up. So now let's answer the question. So thumbs up if the astronomer with the orange, or rather purple, if the astronomer with the purple telescope is able to see the emission spectra, and thumbs down if the astronomer with the orange telescope on a different planet is able to see the emission spectra, or since it's just one, spectrum. Let's get some answers for this one. Thank you, Alexander. You're always on top of answers. I appreciate it. Let's get a few more. All right. I saw someone give a thumbs up to the thumbs down. I love that, but it's probably meant you agree. All right. So everyone says, okay, yeah, it's going to be the viewer that's off to the side, which is good. You seem to have a solid understanding. Nice. Yep. This astronomer on a different world, maybe they're us, and the aliens are the ones with the purple telescope. We're seeing an emission spectrum because our line of sight doesn't have the source directly behind. So we're not seeing the absorption. Instead, we're seeing the emission. And what's interesting is that when you have that direct line of sight, where like the star usually, that's usually what it's going to be, is directly behind the gas, you really can't. Even though the emission spectrum should also be there, it's so much weaker, it's so much less intense that it's hard to detect. Right. So when there is an absorption spectrum, it washes out an emission spectrum. So you can't really see both at the same time. And obviously all it would do is just fill in the gaps, but it doesn't because you know the dominant light is the one that's coming from the hot star. All right. So and then the other one, the astronomer that we left off, we already said they see an absorption spectrum. They don't see a continuous spectrum because the gas is in the way. You would only see a continuous spectrum if you have an unobstructed view of a black body. All right, last topic, the Doppler effect. So far, we've got temperature that we can find out from the spectrum. And also the fact we know it's a black body, right? So we have also a bit of information, right? Because if we see a continuous spectrum, it kind of tells us what we're looking at. We also now realize that we can find the chemical and atomic composition from absorption and emission spectra. Cool. So we got all these different types of information that can be gained from measuring light. Last thing, not the very last thing, but the last thing that we'll cover is we can measure the speed of an object, which is pretty cool. Because if we know what that object is made out of, so if we have some like comparison, so if we know that like, hey, this type of star, and we've seen this type of star before, and we know what its spectrum looks like if that star is not moving away or towards us, then we can look at a twin or a very similar star, and we know well that for whatever reason, usually because of chemical composition, we know it's the same type of star. And we look at it and we see, okay, well now this one looks different. Its color is not quite the same. It's redder than we'd expect. Well, you might think, oh, your instruments just aren't working or whatever. But it turns out the reason is because that star is moving away from us if it's redder, and if it's moving towards us, it's bluer. So this is the way that we can take, kind of like known information from other measurements and then use it to compare to moving objects to find out how fast they're moving and also whether they're moving away from us or towards us. And this whole type of measurement and consideration is called the Doppler effect. So I guess specifically you would call it the Doppler effect of light. And because you can do the Doppler effect of sound as well, it's well known to be done with sound. It's how you can actually make measurements of speed with sound waves. But here we're doing it with light because it wouldn't make any sense to do it with sound because sound doesn't travel through space. So, we use light. All right. So when you think about it, though, if you are thinking about sound, the change in frequency of a wave due to the motion of the wave to the observer is the Doppler effect. And that creates the effect of a siren that's passing by you. It's higher pitch when it's approaching you, and then it drops to lower pitch as soon as it passes by you and then is moving away. So if you have a siren that's moving at constant velocity towards you, passes you, and then moves away, it'd be something like right? So high pitch on the approach, sudden transition, low pitch. So that's a good demonstration of the Doppler effect with a wave, but in that case, a sound wave. Right? So moving closer, high frequency, shifted to higher frequency. Moving away, shifted to lower frequency. All right. So source moving closer, higher frequency. How does the wavelength change? Well, I think you know this one. If the frequency goes up, the wavelength goes down, which means it gets shorter. Okay. And that's actually often the way that this phenomenon is explained is we show the wave and we show that when the source is moving towards you, the waves get bunched together. And that actually creates the Doppler effect. But in general, a source moving closer has higher frequency and shorter wavelengths. Compared to what? Well, compared to when the source is at rest, right? When both you and the source are at rest relative to each other. And obviously, nothing is at rest in space, but what happens is you just have to be moving, neither towards or away. So as long as you're moving like to the sides, like if objects moving towards the left and you're moving to the right, there's no Doppler effect. So that would be a kind of baseline comparison. And then you would compare, to something that's moving partially towards you or fully towards you or partially away or whatever. All right. So we we look at excuse me, take a drink. So I mentioned kind of having that baseline comparison. So let's consider one. So consider the absorption spectrum for hydrogen. So this is a well-known, probably the best known absorption spectrum. Hydrogen is the simplest atom out there. It's incredibly abundant in space. And its absorption spectrum looks like this. It's got absorption lines at like 410, 435, 480, and then another one at like 660. Right. So these are the absorption lines of atomic hydrogen in the visible spectrum. There's other absorption lines outside of the visible spectrum into the infrared. But okay. Bigger energy gaps. Actually, ultraviolet. There might be some infrared ones, but the other well-known ones are ultraviolet. Okay, so and this spectrum as shown is the one that you would see in a laboratory and also from a stationary galaxy. And stationary at least being neither moving away nor towards us, which as far as galaxies are concerned would be considered one that's relatively close to us or maybe in our local group. So then if you compared to other galaxies, so the bottom four spectra are from four other hydrogen-rich galaxies. Which of the other four is moving away from us the fastest? So look at their spectras. Look how they're all shifted. They all experience a Doppler shift manifested in the change in wavelengths. But which of them shows a change that represents movement away? And of those, which is the fastest? Okay. So Fiora mentioned that 1 in 4 are moving away. I think one's moving the fastest. Yeah. So good. Yeah, because 1 in 4 are both shifted in the red direction, which is the direction of movement away. Good. And then you went with one because the shift is bigger. Four is a good guess, okay? But it is one. Nice. Four would be the closest other answer, but it's not the fastest because it's a smaller shift towards the red. So we say that the galaxy is red shifted because that's the type of shift for anything that's moving away. If something is moving towards us, the change in frequency and the change in wavelength results in things becoming bluer. So we call motion towards us as a blue shift. All right. But this would be a red shifted galaxy. And the bigger red shift, the faster the movement. Yeah. And it's pointing out the change, showing how they correspond. Two is actually just the same spectrum, unchanged. And three, by the way, would be that blue shift I mentioned. That'd be a galaxy that's moving towards us, which is actually pretty rare. Most galaxies are moving away from us. We'll talk more about that when we talk about the structure of the cosmos. So the bigger the change in the frequency slash wavelength, the faster the object. All right, and you can do it yourself, and that's it. All right. So how about we finish a few minutes early today, since we made it all the way through the slides? I say it's a good idea. We rarely get the opportunity. Cool. And just remember, we will have a quiz tomorrow, which is our early Friday essentially, because it's our last class of the week, and it's going to be on this chapter. So we will have a chapter 5 Zoom quiz right around the beginning of class. So expect it, about 5 minutes after class starts. And I'll see you all then. Bye for now.